Good evening, everyone. I am Elena Nieddu from Roma Tre University. I'm a PhD student in computer science, and I work at the Codice Ratio research project. So this talk starts with some disclaimers, or rather apologies, because first of all, I'm not a paleographer. So most likely, I will use incorrect terms. Please forgive me, and correct me as well. The second disclaimer is that the case study we're working on is actually not a papyrus. It's actually parchment for the 13th century. However, since this approach is applied directly on digital images, we believe it can be interesting as well for people working with digitized papyri, because we're always talking images. And also, I think the text we're working with share some similarities. So what's the Codice Ratio research project about? The project was born in the engineering department from Professor Paolo Merialdo, who is an expert in search, information retrieval, information extraction, and knowledge extraction in general from web sources. And the question we're trying to answer is, can we apply these techniques to the context of archives, of historical archives and historical sources, so that we can do for the context of history, for example, what we're doing with the internet, with the research search engines, and things like that. The first step of going towards this was working with images, because one major difference is that most of the content that is in historical archives is digital images. And to a computer and to a, for example, to a natural language processing algorithm, these two sources are incredibly different. So what we first did was to try and find a way of having a handwritten text recognition system that, that could help us find the information. But this also meant collecting data, and I believe that in this process, the data we collected and some of the approaches we have experimented with could be relevant for the creation of paleographic thesauri. So our case study are the Vatican registers. The Vatican registers are a very important collection that is preserved in the Apostolic Vatican Archive, which was formerly the Vatican Secret Archive, and is a collection of copies of the official correspondence to and from the Holy See. So everything that the Pope was writing in a formal occasion was then transcribed on these registers and preserved. We're focusing on sources that are between the 12th and 13th century. And they present we will see it, they present a pretty regular, highly formalized handwritings. It has many abbreviations that are interesting to study and to look at. And it has a very formulaic language and style. And most of all, it's also a very large, it's a pretty large collection. The whole collection, which spans more centuries than the one that we are accounting for, is about 18,000 pages. So, for example, having a large-scale tools for large-scale analysis could be very, very useful. So this is the documents that we're working with. This is an example with the transcriptions. You can see abbreviations that are between parentheses, within brackets. And so we ask ourselves, how can we get from the image? Oh, how do I point? Does it work? Okay, okay, there it is. So how do we get from this to this? And how can we do it, especially in an efficient way? Because training a neural network, for example, in general, a machine learning system is as good as how much data you're able to produce and as good as the data you're having, which means that you are going to involve a paleographer and have him or her transcribe, at present, thousands of images, because a machine learning system requires thousands of examples in order to be able to generalize. The graph you see here is a graph that has on the x-axis how many words, and on the y-axis occur how many times. So basically, this is a frequency count, and we are trying to estimate how many words occur how many times, because this is also a good estimate for understanding how, for example, how many pages would we need to transcribe if we were recognizing by word or by line. And what we see here is that only more, this is too small, I'm sorry, only less than 10, this is about 100 pages. Only less, in these 100 pages, only less than 10 words occur more than 100 times. You see it here like a backwards line, but this is actually an inverted exponential. So it's exponentially more unlikely that you will find a word. And also, these are the least interesting words sometimes, because they're usually conjunctions or something like that. Whereas here you have nouns, names of people, and all of the other words that make the discourse. So we asked ourselves, how can we do this in a way that's sustainable, that's easy, and that can be reproduced when you don't have a lot of time or a lot of resources? And we tried a crowdsourcing approach. That is, we involved both experts and non-experts to label single characters, single symbols from a set that was considered relevant by the paleographers. So here, and we did it in two ways, two different runs. Here in the green box on top, you see the example that were chosen by the paleographers. So it was expert curated, but there is a very reduced, it was like 10 symbols here. For the sake of brevity, it's just 4. And it was 10 examples from where the relatively untrained people, such as high school students, were asked to match the most similar characters. So it's a pretty simple. We try to make the task as simple as possible. And so we had 2 runs, as I was mentioning. Here on top, you see the first version, and on the bottom is the second one, is the second version. That's because after we ran the first test, it was only 100 students, only. We asked them for feedback, and they told us that sometimes they were unsure on whether to click on something or not. And they weren't wrong, because take, for example, this element here, and I will, okay, so as well. Without any proper context, it can look like an abbreviation. So it looks like that Tyronian note in these kind of scripts. And so you may be uncertain as to where mark it or not, but it could also be a part of another character. It works as well for this one, that is I and then O, but it could also be that there is another part of the character here, so it could actually be N-O. And so you would induce error because you're not giving enough context. And so, what we realized, what we did then was to provide the whole word in the second run, so that they could have some context, and this kind of error could be prevented. And it was so we had feedback then again, and they told us that, well, maybe it was also more stimulating as a task. And so, and this time was 500 high school students, and in a few weeks' work, we were able to collect more than 40,000 annotations for 32 different symbols. Of course, because we were working with people that are not experts, there was high redundancy. So we didn't trust one single answer, but the same question was posed to many, many different people. And then when there was consensus over a single symbol, we would ask another. So we use this for our transcription system that is briefly shown here as a pipeline. So basically, we will see more in the detail how it works, but there is a step of pre-processing when we start from the original image and do some cleaning, separation of the text from the background, which can be noisy. And then we isolate the single words, and then inside of the single words, we try and find characters. Then we have a neural network, which was trained with the example that I have shown you earlier. that is able, it's not only able to tell which character it is, but it's also able to distinguish whether a segmentation is good or bad. And then this doesn't challenge all the ambiguities, which is why we don't have only the visual knowledge, but we add to this visual novel statistical knowledge of the language. We had some text corpora, and we included them so that we could make some computation on the frequencies of the occurrences of the character. So we have a knowledge of how likely one character is to follow another sequence. And then in the end, this gives a transcription. So these are the pre-processing steps. This is one of our pages. The layout in this case is not that hard. And so we just extract the part that is important to us, that is the central text, and we clean it from the background noise. Then we extract single words, and then for each word, we actually, as you can see, we don't segment characters as they are, but we over-segment them. That's because when one tries to segment this kind of writing, and in general handwritten text, cursive text, you often incur in what is called series paradox. That is a chicken and egg situations where you would like to separate one character from another, but in order to do that, you want to do that because you want to recognize them. But you need to recognize them first if you want to separate them. So it's a bit of a paradox, and so this is our approach to it. That's the cost of not training a model recognizing words or lines, that you have to find the character inside of the word. So we use a data structure that is a directed acyclical graph. I'm sorry if this is technical. And which represents all the possible alternatives. We also call this kind of segmentation jigsaw segmentation because it's a bit like of a jigsaw puzzle, where you try and match some elements and see if they actually produce a word. And each of these pictures is then classified by our neural network. So as I was saying earlier, it has two different types of outputs. The first one tells you its confidence that it is a character or it isn't, because as you can see, there is definitely parts in here that are not characters, like this one or this one. And so we want to get rid of them because they do not produce any information for us. And then it's able to classify. So we have 32 different symbols. And overall, the network is 96% accurate on its predictions, which means that in 4% cases, and it's actually it's high when you think of a large scale. It can be wrong though. So what we get after the first pruning is that some of the edges are gone, some of the part of the picture that are obviously not characters, but we're still left with some ambiguity. Because, for example, there is no way, just by graphical analysis in isolation, to tell whether this one is a D or an O, or whether this is a D or an O, or whether this is a I or a T, for example. Which one? If you're just looking at the picture, just like the students, you can't tell. And so what we do is that here we introduce knowledge of the language to disambiguate. We have computed statistics on substrings coming from latent corpora from papal bowls. And so, for example, if we choose this path of transcription, which is also the correct one, we are going to ask the statistics how likely it is to be a Latin word. And then we try different paths. For example, like here, we are choosing to interpret this as a D and this is an I. And so we're going by D, A, I, D. And we're also asking the likelihood of this word as well. What happens is that usually the correct word is higher because, for example, died or D-I-I-D are very unlikely in Latin. They do not occur, whereas dato is a word that does occur. And for evaluation, we take it, so as you can see, we don't have only one transcription. We have many transcriptions that the system produces. And so we can take into account only the first one, the best ranked, but we can also take into account, for example, the first 3. These are our results. This is top 1 and top 3, and this is Tesseract 4. This is word level accuracy. And Tesseract 4, for those who don't know, is the Google OCR engine, the open source one at least. And when it comes to words, if the word is correctly segmented inside of the page, we are having 70% perfect accuracy, and we get up to 90% with at most 2 spelling errors with the top 1. And with the top 3, we have 80% accuracy. It means that in the top 3, in the 80% of the cases, there is the correct word. This can be used back. We think that this can be used back, for example, for analyzing scripts. And there is an advantage. Like, you could do only similarity from images. You don't need transcriptions for that. But it can be interesting to see how, for example, the same word of the same set of characters occurs abbreviated and unabbreviated when, for example, the writer is going to use a specific symbol and when it's not going to, and which writers do that. So, and of course, we don't expect the machine to do that, but this is a good tool for collection and the creation of thesauri. So, for example, here we have pro, and it occurs unabbreviated and then abbreviated. And here we have et, and we have mostly when it's just the connection is just et abbreviated, but sometimes it occurs together with other characters, and sometimes it's just part of a verb. So you can do quantitative analysis or collect more specimens in order to create a thesauri of symbols and the word. So future applications, we're planning to extend the same pipeline to different writings. So the only constraint is that you need to have a digital image. And then this could be a start for the collection of paleographic thesauri. This is the full team, and which I'd like to thank. And Serena is very sorry that she couldn't be here. And I thank you for your attention. And